Welcome to day three. Over the last two sessions, we found how temperature and pressure change with altitude. Today, we close the loop with the third and final piece of standard atmosphere density. This one is arguably the most important of the three for performance because density is what actually shows up in the lift equation, the drag equation, and the engine thrust calculations. So less dense air means less lift for the same speed. That's a fact. Uh, every pilot and every aircraft designer has to work around. So once we finish today, we will have completed the full standard atmosphere model, temperature, pressure, and density. And from day four onward, we move into basic fluid dynamics. Right. Here is today's formula. Rho equals rho 0 times the quantity 1 minus L H over T0 all raised to the power G over R L minus 1. So notice how similar this looks to yesterday's pressure formula. Same bracket 1 minus LH over T0. The only difference is the exponent. Instead of G over RL, it's G over RL minus 1. Right. Let's define. Let's define the symbols. Rho is density at altitude in kilometer per cubic meter. That's what we are solving for. Rho 0 is sea level density, and the ISA standard value is 1.225 kilograms per cubic meter. That's a number worth memorizing. It comes up constantly in aerodynamics. So L, T0, G, and R are exactly the same constants we used on day one and day two. So nothing new to learn there. And H is altitude in meters, same as always. The ISA density variation equation here again. See this? So rho density at altitude H, standard value meaning unknown, what we solve for, right? Then yes. Rho 0, L, T0, G, R, and H, right? So here is a shortcut. We already calculated G. We already calculated G over RL on day two. It was 5.2586. So today's exponent is simply 5.2586 minus 1, which is 4.2586. Write that down. It's your density exponent for every problem. So the working formula becomes rho equals rho 0 times times 1 minus LH over T0 raised to the power 4.2586. So basically, think about what density actually means. Okay, it's how many air molecules are packed into each cubic meter. As you climb, the air isn't just colder and under less pressure. It's also more spread out. Fewer molecules per cubic meter means lower density, which means less air for your wings to push against and less oxygen for your engine to burn. Right. So one subtle point, because the exponent here 4.2586 is smaller than pressures 5.2586. density actually falls a little slower than pressure does, percentage wise, but both fall faster than temperature. So which only had a lapse rate straight line. So can understand. Okay. So now we can move for the worked examples. So for example one, let's run the same two altitudes. We have used all series. So you can see temperature, pressure, and density side by side. So first 3,000 meters, then 10,000 meters. See step one, write the formula rho equals rho zero times rho zero times 1 minus LH over T0 to the power of 4.2586. Step 2, unknown. So rho 0 is 1.225 kilograms per cubic meter. L is 0.0065. H is 3,000 meters. T0 is 288.15. So step 3, inner brackets. So which we actually already calculated on day 2. Right. LH over T0 equals um, 0.0677. So 1 minus 0.0677 equals 0.9323. So step 4, raise 0.9323 to the power 4.2586 on your calculator. That gives approximately 0.7420. Right. Step 5, multiplied by rho 0. So 1.225 times 0.7420 equals approximately 0.909 kilograms per cubic meter. So at 3,000 meters, the air is about 74% as dense as it is at sea level. So meaning a wing at this altitude generates noticeably less lift for the same airspeed, right? So now let's move for the next worked example. Find the air density at 10,000 meters airliner cruise. Okay, same steps from day 2. We already know the inner bracket. So 1 minus LH over T0 equals 0.774. Raise 0.774 to the power 4.2586. That gives approximately 0.3367. So multiplied by the rho 0, 1.225 times 0.3367 equals approximately 0.412 kilogram per cubic meter. So that's only about the third of sea level density. So this is exactly why airlines need long runways and high takeoff speeds relative to cruise speed at low altitude. So, but can cruise efficiently at high speed once they climbed into this thin air. Less density also means less drag. So three mistakes to avoid. First, don't confuse the density exponent with the pressure exponent. Okay, pressure uses G over RL, density uses G over RL minus 1. So mixing them up is a single most common error on this formula. So second, you can reuse your day two bracket calculation 1 minus LH over T0 since it's identical for both pressure and density at the same altitude. Just don't reuse the exponents. Third, the sanity check. So density should always come out less than 1.225 kilograms per cubic meter within this altitude range. And it should be a small positive decimal, typically between about zero point 0.3 and 1.2 for the atmosphere. Right. Let's recap. Rho equals rho 0 times 1 minus LH over T0 to the power G over RL minus 1. So which is 4.2586. Rho zero is 1.225 kilograms per cubic meter. So valid from sea level to 11,000 meters. Your practice question, uh, find the density at 5,500 meters altitude. So same steps as always. Drop your answer in the comments. So that completes the standard atmosphere trial. So temperature, pressure, and density. Days one through through day three. So tomorrow, day four, we start a brand new category, basic fluid dynamics, beginning with the continuity equation, the rule that explains why air speeds up when it flows through a narrower space. See you then.